Okay, I think we'll get started. If you're coming from the GNL project, then I encourage you to look at the introductory video in this playlist to see if this is the right series for you. Otherwise, we're going to talk about apparent forces, and this is going to pick up a bit from what we talked about last time. And we're going to introduce the idea of a centrifugal force and actually an application to a centrifuge that you might be familiar with in biochemistry. Okay. So let's imagine here now this setup that we've looked at before, where this toy airplane is attached to this cable, and this is going at a constant speed, but we know now not a constant velocity, because the cable is going to direct this inward. It's going to change its direction. So velocity is a vector, so magnitude and direction. We're going to change the direction. So therefore, we need an acceleration called the centripetal acceleration. And what's going to supply that is the tension in this cable, and that's going to be supplying the F equals ma from Newton's law. And we know in this case the force is a centripetal acceleration, or a centripetal force. There's our formula. Oops, just over R. There's our formula for the centripetal force. Now, let's imagine instead of a little eyelet here, we're holding onto this string. So it's spinning horizontally in this horizontal plane, and we're holding onto it. Well, if this is a downward tension here, directing that inward, the centripetal force is pointing inward, we're going to feel the reaction force on this end of the rope, right, in this direction. And so there'll be an equal but opposite tension pull on us, pulling us outward. And that, what we feel there is what we call a centrifugal force directed in the opposite direction as the centripetal force. So centripetal force pointing inward, centrifugal force pointing outward. And we're feeling that pulling us outward. Well, let's take this horizontal plane and let's turn it in Earth's gravitational field. So we're going to break the symmetry of this. This has perfect symmetry all the way around here. There's no real difference where it is in this circular path. Well, here there definitely is. So we're moving in gravity, and so we're going to have two special places here. The labeled A here as the nadir, the bottom of this arc as this spins around, and then B, the zenith. So imagine we've got some mass and we're swinging it this way. We're holding onto the cord and we're swinging it this way, vertically, in the vertical plane. Okay, well, let's look at these two special points. All the other points in between are just sort of continuous from A to B and B to A. But let's look at these two extremes, the nadir and the zenith. And let's draw the free body diagram for this mass we have on this string. So we put this mass on this rope. We're down at the nadir, and let's draw the free body diagram. Well, it's going to have its weight. That's always pointed downward. And then we need that centripetal force pointing upward, and that's coming through the tension in the rope. Now, we need to accelerate it upward, or it's got to be upward now because we're at the bottom here. So we're always directed towards the center here, directed inward. And it's got to be moving, so it's got to be accelerating. So this tension has to be greater than the weight. If the weight was greater, then we'd get the mass would accelerate downward, but it's accelerating upward, so the tension is greater. Now let's go up around now to the zenith, and let's draw the free body diagram. Weight still pointing down. Weight always points down. Now the tension has to pull down. We have to accelerate this downward, so it's in the same direction as the weight, and it's much less because if we were pulling with the same force we were pulling here, but downward, now that the weight's helping us, we would have a much bigger centripetal acceleration. So we don't. The centripetal acceleration stays the same. So the centripetal force then is the centripetal force is the net force here that were used to pull this either up here or pull it down from the top. So if we think about what are we experiencing if we're holding on to this, when we're at the nadir, we're feeling a much stronger force that we have to pull back up with. And when we're at the zenith, we're feeling less that we have to pull down with. Okay, well, let's take this situation, but now move us from hanging onto the rope while it's spinning, and let's put us in this box here. So let's imagine we're in some kind of carnival ride, and we're in this box. We don't have to worry about how this works, but we're just going to be in this spinning box. And let's imagine we first step into it. It's not moving, and we stand in this container. And we're, let's say 90 kilograms, then we would feel the weight associated with 90 kilograms, so 90 times 9.8. And we would feel that because the bottom of the container is pushing back against us with a normal force equal to that weight force. And so we feel our weight because we're being pushed on by the floor back up against that. Well, now let's get this carnival ride moving, and let's think about the two different places. I guess I drew the zenith here, so let's think about that first. So now we're in this box. We're not attached to the box, right? So the box is being pulled. The box is accelerating. So when we're standing here, the box is being accelerated away from us. It's accelerating away from us. So we're going to feel a little bit lighter. Now, we're not going to come off the floor necessarily, but we're going to feel lighter. We could come off the floor, but let's say this is not going super fast. So we're actually going to feel a normal force that is much smaller than the weight force. Notice it's a bit counterintuitive. It's certainly related to this, but you want to tell yourself the story of this, and even draw on your own life's experience. You're going up over a hill, you're going to feel a bit lighter. Now let's bring it down here. Again, your life experience, when you come down on a hill and you're in a car, for example, you're going to feel like you're pushed into the seat a little bit more. Well, let's draw this picture. Okay, now we're standing on the ground, and the container is being accelerated upward into us. So the normal force is now bigger than our weight force. And so if we look here, the normal force is bigger. So our apparent force, and in this case, this is called an apparent weight, okay, because we're like augmenting what we feel as the weight. And I think the word apparent is helpful because you can kind of think about it as it's not really the weight, but it's what you would experience, what it would appear you are. Right? So it's not a real weight force, but it's this apparent weight. Okay, well, let's use we know our formula for centripetal acceleration, and let's calculate the magnitude of that. Let's calculate the magnitude of the apparent weight. It is going to be the magnitude of the vector difference between the weight and the centripetal force. And so if we write this out, if we just write it out, weight is always mg, right? So mg. And then if we're at the nadir, these add together, right? Because the centripetal force is working upward, it's against the weight, and since this is negative, they're going in opposite directions, so because it's negative, they're going to add together. And then at the top, they subtract from one another. And so that's at the zenith. So we feel lighter at the zenith, heavier at the nadir. Now notice, we're always going to feel heavier at the nadir, and we'll feel lighter at the zenith. In fact, we could be moving fast enough that act counters the weight, or it's even bigger than the weight. And in that case, we would come off the floor. And if it was really going fast, we would get pushed up against the top of the container. Right? And we would be experiencing the centrifugal force pushing us outwardly. So let's use that as an example in the centrifuge that you may have seen in biochemistry. So in modern, in centrifuges, we have this test tube or tube, and we can put a solution in. Maybe in biology, we might lyse a cell and put the pieces of the cell in there and try to get the different organelles to layer out differently. Or even in biochemistry, we can do this with proteins, with these ultracentrifuges. And it seems crazy that you could take two proteins and separate them by weight. So if we had just put them in the test tube, really by density actually, if we just put them in the test tube, the at the protein level, they're just so small that we're not going to get the more dense one to go to the bottom compared to the less dense one just sitting on the lab bench. But if we start to spin this, and with these centrifuges, we can get a centrifugal acceleration that is 1,000,000 g, so 1,000,000 times that of gravity, so 9.8 times 10 to the 6th meters per second. And the gravity is negligible then, so our apparent weight is going to be solely the centrifugal acceleration. Now, for these proteins, they're in this solution, and so it's not like a free fall. It's like falling through a thick fluid. And so we have a drag force that's opposing us. So if we draw the free body diagram for this protein, it's going to have this apparent weight pushing it out this way, and it's going to be facing a drag force. Now, the exact form of the drag force depends on the shape of the protein and how it interacts with the solution. But as an approximation, we can treat it as a spherical, and this works pretty well for globular proteins. And if it is spherical, we have something called Stokes' law, which we run into this, but in this case, you don't have to worry too much about it. But with Stokes' law, then we can express the drag force that's experiencing when we reach this terminal velocity. So the protein takes off, very quickly it reaches its terminal velocity. Right? And that happens when the drag force equal and opposite the weight force. Well, we know the weight force is this, the drag force is this, so we could set those equal to each other and then solve for the terminal velocity. And so let's do that. Solve for the terminal velocity. And I get my G prime up in here and I get mass. I'm going to adjust that to density. So we can just do the volume of a sphere and work this out such that we get a formula that involves what we really need to worry about here is the G prime and the density of the particles. So we can see that the velocity of the particles are proportional to the density, which we would expect, and the G is the multiplying factor. So sitting on the lab bench with 1 G is just not enough difference to separate these. But when it's multiplied by 1,000,000, then small differences in density become really big because it's being multiplied by this factor of 1,000,000. And so the heavier, or the more dense, I shouldn't say heavy, the more dense proteins go to the bottom or the edge, the outer edge of the test tube, more than lighter proteins. So you have this layering of the heavier proteins at the bottom and the lighter proteins at the top, and then just the supernatant at the very top, the liquid. Okay, and so this is an application. We don't have to worry too much about this in terms of the physics course here. We want to know these formula for calculating the apparent weight. We want to understand how to draw the free body diagrams in each of the positions here. And then the centrifuge was just an example of how this is utilized in our other science courses.